Thank you. Hi, I'm Marco Lancini, and today I'm going to talk about social authentication and the implementation deployed by Facebook. First of all, let's start with a little introduction about myself. I graduated in Engineering of Computing Systems in 2013 at Politecnico di Milano, and actually this talk is based on my master thesis. And since then, I'm a security researcher at Sheffield, where I focus my work on different aspects of computer security. My Twitter handle is Lancini Marco, so if you want to get in touch, please do. Okay, let's start. First of all, why doing research on social network? Well, for their huge user base, we have now seen that Facebook has reached and passed the 1 billion active users. That roughly corresponds to 1/7 of the entire world population. Then, for the massive amount of personal information these networks have, and also for the widespread adoption of single sign-on services. For all these reasons, these networks have become an appealing target for online crime. In the last years, we are witnessing the growth of identity theft and of spamming and phishing campaigns. And one of the latest trends highlights how traditional underground economies have shifted their focus from stolen credit card numbers to the selling of compromising social network accounts that are sold for the highest prices. And in a network like Facebook or also Twitter, 97% of malicious accounts are compromised ones, are not fake accounts created by the attackers. So, high-end services like Google, online banking, LinkedIn, and many others in the last few months, in order to prevent adversaries from compromising accounts using stolen credentials, started adopting the so-called two-factor authentication, where users need to provide two separate pieces of information in order to authenticate. There is the traditional standard factor, the knowledge factor, the combination of username and password, and then it's added a second factor that usually is something the user possesses. It can be an hardware token, and the user needs to prove its physical presence in real time during the authentication process, but could also be a one-time code that is generated by the backend of the service and sent to the user via SMS, voice call, or via an app. Well, with this approach, the risk of an adversary of acquiring the both piece of information is very low, because an attacker will have to acquire both the username and password and also the physical token or the mobile phone of the victim. But this approach presents some drawbacks. If, for example, the service decides to use an hardware token like many banks do, well, first of all, we are dealing with a physical piece of hardware that needs to be manufactured and delivered to all the users. So this is present a cost for the service. And also, this piece of hardware is seen as inconvenient for the user that have to carry it with themselves wherever they go. At the same time, if instead the service decides to use an SMS delivery system, for example, well, we all know that SMS are sent in plain text and can also be easily intercepted and forwarded. If the mobile phone of a victim is also infected with a malware, this malicious application can easily intercept all the incoming messages and forward it to a third-party number, even without the user even noticing. And lastly, but not for importance, phones are easily lost and stolen. So if an attacker can obtain physical access to a phone, he can simply read the SMS and look to the code. But what is said is that one of the latest studies shows that roughly 95% of end users are either unaware of two-factor authentication mechanisms or actively choose not to use them because they are seen as inconvenient for them. So here, the challenge is to balance strong security with usability. And a new emerging approach consists in authenticating users via a method called social authentication that is suitable especially for social networks. Here, a social CAPTCHA is presented to authenticate a member of the service. A social CAPTCHA can be one or more challenge questions based on information available in the network itself. And we will see in a little bit how this works. But let's think about it. This approach can eliminate the key issues of traditional CAPTCHAs that are incredibly hard to decipher also for humans. We all struggle with CAPTCHA in our daily life. But these CAPTCHA are also vulnerable to human hackers, if you want to call them, because these CAPTCHA are only meant to defend against automated systems. An attacker can rely on CAPTCHA farming techniques in which he can employ an algorithm to temporarily divert the CAPTCHA question to a human user who can solve the question and return the answer to the legitimate service. So if cheap human labor can be utilized, for example, Amazon Mechanical Turk, where people can pay other people to take tasks online, well, this approach can be rendered completely ineffective. Facebook implemented its own version of social authentication. In this case, the second factor isn't anymore something the user has, but becomes something the user knows as his friend. The user's credentials are in fact considered authentic only if the user can correctly identify his friends. The idea behind this is that only the legitimate user can recognize his friends, whereas an attacker in any point of the globe who might be able to gain access to the credentials of a user via phishing, Trojan, keyloggers, or any other means, well, this attacker still can't know who the friends of his victim are. And actually, this mechanism is triggered when a login is considered suspicious by Facebook, namely when it comes from a geographic location or a device that have never been seen before. Let's see briefly how it works. If the login is considered suspicious by Facebook, right after the standard password-based authentication, Facebook shows the user a few pictures of his friends and asks him to name the depicted person. In particular, the social out is composed by 7 challenges, 7 pages, each of which contains 3 photos of a friend of the user and 6 possible names, 6 possible answers. The user needs to correctly identify the depicted friends and choose the correct name. The test is composed by 7 challenges, so the user must answer correctly at least 5 of the 7 challenges. And all this process must be completed in a time frame of 5 minutes maximum. In this talk and also in the third model proposed by Facebook, we will refer to a friend as a people inside a user online social circle. A friend is anyone who has access to the information used to create the social authentication test itself. So this mechanism is considered safe against adversaries that have, yes, stolen credentials, but are strangers. They are outside the victim's social circle. At the same time, this mechanism is not guaranteed to be safe against close friends, family, or any other tightly connected network, like a university, because in these cases, any member of this strict connected network has enough information to solve the test for any other member in the circle. So we started performing a vulnerability assessment of this mechanism. And we started asking us if photos were randomly selected by Facebook. We took a sample of about 3,000 photos taken from real social authentication tests, and we inspected them. First, we inspected them manually, and using this manual inspection, we were able to detect at least one face in 84% of these photos. And then we processed them with an automated software, with a face detection algorithm. And these algorithms were able to detect at least one face in 80% of these photos. We then took another sample of photos taken randomly from Facebook, not from social authentication test. And we analyzed them manually, and we saw that only 69% of those photos contained at least one face. So the baseline number of faces per photo is lower in general than in the one used to create this authentication test. So we argued that Facebook employs some sort of face detection filter to select photos with faces in order to create this test. Just remember the photos taken from this test. 84% contains a face identified by a manual inspection. 80% of photos contain a face identified by software. Well, these 84% with photos with faces makes the social authentication solvable by humans, make it usable for the user of the network. But the 80% of photos with faces that can be detected also by a software led us to ask if an attacker can bypass this mechanism automatically, positioning himself inside the victim's social circle, so gaining all the information necessary to a software to break this system. We then identified 2 types of attackers, 2 kinds of attacker models. Here, an attacker is someone who has stolen the credential of a user, and this is also the reason because this mechanism was deployed by Facebook. So an attacker can obtain the credential in any means, depending on his skills and motivations. But then we can have two different types of behavior. We can have a casual attacker that is interested in compromising the greatest possible number of accounts, and for doing so, it relies only on publicly available data. And we can also have a determined attacker that is interested and focused on a particular target, and who proactively tries to infiltrate the victim's social circle, so to collect as much private data as possible. Then we calculated an attack tree, I hope you can see it, to estimate the vulnerable Facebook population. Initially, an attacker required access to the victim's friend list. 47% of the people on Facebook leave their friend list public. And even if it's not the case, a determined attacker can try to befriend his victim. Now, studies have shown that people on Facebook tend to accept friend requests even from unknown people, with 60 to 90% chance of success for an attacker. And in this work, we took a conservative average of 70%. So up to now, a determined attacker has a combined 84% chance of success so far versus the 47% of a casual attacker. Then this attacker needs to focus on the photos that are the core of the system. Ideally, the attacker can gain access to all the photos of all the friends of his victim. Then with a probability of 1, he can solve any test because he knows all the photos that can be used for creating the test. In reality, this is not so simple because an attacker might gain access to only a subset of the photos of a subset of the friend of his victim. And our study revealed that 71% of the users on Facebook expose at least one public photo album. Again, a determined attacker can try to befriend the friends of his victim with 70% chance of success. So at the end of this step, the determined attacker has, on average, at least one photo for the 77% of the friend of his victim, whereas a casual attacker has only for 33%. Then the next step is to extract tags from these collected photos, so to match faces to UIDs. A UID is a unique identifier that represents a Facebook account. So attacker needs to match faces with profile on Facebook, so to train a facial model able to respond to the test. By analyzing the photos contained in our dataset, we found that 17% of these photos contain tags. So 17% of these photos can be used by Facebook to generate this test. And by collecting these tags, we were able to match UIDs to faces for the 42% of the people in the friend list of the respective victim. So a casual attacker can obtain the 42% of the information needed, ideally, to break this test. We cannot calculate this percentage for a determined attacker because we relied only on publicly available data, but we will see that we have simulated this scenario. So having calculated the probability of success of our attack, we then designed and implemented an automated system able to break this mechanism. Our system was composed by five steps. In the first one is the crawling on the friend list. Given the UID of the victim, a crawler retrieves all the UIDs and names of the friend of his victim. Then, in the second step, a determined attacker can try to use social engineering techniques. He can try to create fake profiles to send friend requests to the friend of his victim. And doing so, he can expand the attack surface, as we have seen, because it can greatly increase the number of photos that can be reachable in the third step, that is the photo collection one, in which we download all the photos we have access to. Of course, a determined attacker who has among his friends, the friend of his victim, can also have access to their private albums, so he can reach a greater number of photos than the one only publicly available. Then the fourth step is the most important, is the modeling one, in which each downloaded photo is processed and analyzed by a face detection algorithm that tries to detect and extract all the faces present in those photos and to match each face with its closest Facebook tag. So to create a label data set which contains for each friend of the victim a set of his faces. This label data set contains then for each friend a set of his faces. These faces are then used to create a facial model for each one of the friend of the victim. These facial models are then used to train a face recognition classifier. Classifier that is queried in the last step, the last one, in which when Facebook challenge our system with a real social authentication test, we can collect all the photos presented in the 7 challenges, extract the faces present in those photos, and use these faces as our testing data set. And then we can choose the response, the name that exhibits the more consensus coming from our classifier. As I said earlier, briefly, we collected data as casual attackers will do. We relied only on publicly available data. Disclaimer, we have not compromised nor damaged any user account, but our dataset contains data about real Facebook users, including their UIDs, names, profile pictures, and friendship relationships. Through public crawling, we collected data regarding almost 240,000 Facebook users, and we saw that 71% of these users have at least one public available album. So we refer to them as public users. The remainder of the users keep their albums private, but the 38% of the remainder corresponding to the 11% of the total is still reachable by our system because their faces were found in the public photos of one of their friends. This is the case in which, let's say, user Alice keep all her albums private, and also Alice doesn't accept friend requests from unknown people. But if Alice is friend with Bob, and Bob has a public album in which Alice is tagged, or even if Bob accepts friend requests from unknown people, then also Alice is implicitly exposed to crawling. And this highlights how it's difficult to control the data shared on a network like Facebook. So we refer to them as semi-public users. And the remainder of the user, that 18% of the total, is labeled as private because they keep their albums private and their face were not found in any of the public albums of their friends. So the public users led us to almost 1 million albums, totaling 60 million photos and almost 2 million tags. We use this data as our data set for a couple of experiments. In the first one, we impersonated a casual attacker. We created 11 fake accounts on Facebook, and we friended random people. So we can't solve social authentication for these accounts because we don't know the friends of these fake accounts. We befriended random strangers on Facebook. Then we used Tor to automate the triggering of the social out. As I said earlier, the social out is triggered when a login is considered suspicious. So we exploited the geographic dispersion of the exit nodes on Tor, thus to be appearing logging in from different locations in a very short period of time. And then for the core, for the face recognition module, we opted for a cloud service, namely face.com, that has now been acquired by Facebook itself, and it's the core of its photo tagging engine. So this highlights the accuracy of this software. For the training data set, we use the data extracted from the friends of our fake profiles, and we collected 127 real social out tests, and we use it as testing data set. To be sure about the correctness of the answer provided by the face recognition module, we also manually inspected all the results proposed, and we saw that in the 22% of the cases, the tests were automatically solved, in the sense that at least 5 of the 7 pages were correctly answered. In addition, in the 56% of the cases, the attacker would only needed a couple of guesses, because the system were able to correctly answer 3 or 4 of the 7 pages. So adding up 78% of the cases in which the attacks were automatically defeated, or the attacker can gain a significant advantage. We further analyzed the pages that failed to provide a correct answer, And we saw that in the 25% of these pages, there were no face in the photos presented by Facebook. So these pages represent a problem also for a legitimate user, which can't identify a friend if a face is not present. In another 50% of the cases, there was a face, but it was unrecognizable by the software because it comes from a photo of pure quality. And in the remainder of the cases, in 25% of the remainder of the cases, there was no face model found for the detected face. So this is the case in which a casual attacker might lack the information needed to successfully solve a test. So we also performed a second experiment in which impersonated a determined attacker. We use a simulation, and for the face recognition module, this time we opted for a custom implementation based on the graphic libraries OpenCV, because we wanted to evaluate the accuracy of the system, and also to define the number of faces per user needed to successfully train our classifier so that it can be able to successfully solve any test. So at each iteration, we trained our system with an even increasing number of faces per friend, starting with 10 faces per friend and increasing. And at each iteration, we generated 30 social authentication tests from photos not used for training. What we saw is that even when a scarce number of faces is available, even in the order of 10 faces for each one of the friend of the victim, the attack is always successful. The system is able to solve correctly at least 5 of the 7 challenges. Moreover, in addition, when we reach a certain threshold that is around 100, 120 faces per friend, the attack is even more robust because all the 7 pages out of 7 were correctly answered. So if the attacker can position himself a victim social circle, he can easily defeat this mechanism. Then there is the problem of the time constraints. Well, the time required for both on-the-fly training and testing remains well under the 5 minutes limits imposed by Facebook. So also the time is not a problem for such a system. We informed Facebook of our study. Facebook acknowledged our results, but stated that the social out was deployed to raise the bar against large-scale phishing attacks and was not designed for small-scale or targeted attacks. For these reasons, we proposed to Facebook a redesign of this mechanism. We had the idea to build tests from photos of pure quality, namely photos in which state-of-the-art face recognition software can detect the presence of human faces, but cannot identify them because these faces are not clearly in front of the camera, for example. So we propose an authentication scheme that can easily be solved by humans, but is robust against face recognition software. We created a web application that simulates the mechanism deployed by Facebook and conducted a user study where we asked humans to solve a test with photos of mixed quality. We defined 3 categories of photos. We have the simple one, which is our baseline category as it replicates the existing mechanism deployed by Facebook and which contains photos in which faces are clearly visible, clearly in front of the camera, and also software has no problem identify and recognize those people. Then we have a medium category, and this contains the photos used in our revisited approach. In this case, the faces are present in the photo, but are not clearly visible, because they can be, for example, slightly turned from the camera, they can wear glasses or a mask or something. Now, the legitimate user has no problem identifying those people, provided that he knows them in reality. Here, a software instead has problems identifying those faces, as we saw in the casual attacker experiment. For photos with pure quality faces cannot be used by a software. And then we proposed also a difficult category in which faces are not present at all. And we wanted to measure how effective people are at recognizing their friends even when their face is not present. Now, in these cases, a human can rely on other factors that a software cannot. For example, it can use secondary features like the hair of its friend. It can use associative information. It can recognize a pet or an object depicted in those photos, or can use memory retrieval. The user can recognize already having seen the photo in one of the albums of his friend. Actually, our software cannot rely on these things. So we created a Facebook application that replicates the social authentication mechanism of Facebook, and we required users to identify their friends and complete a questionnaire. Now, we had the problem to recruit users. We started exploring the possibility of using Amazon Mechanical Turk, but asking the users on Amazon to install a Facebook application or redirecting them outside Amazon, even to fill out a survey, violates the Amazon terms of service. So we had to drop this way. Then we thought about gamification, but it didn't pay so well neither. At last, we thought about prize, and then we see some results. We promised a prize for the person who took the greater number of tests. And actually, we asked our users to install a Facebook application. If the user grants the permission, then we can start collecting all their friends, and for each one of the friends, again, collect all their tags in which they are depicted. And then, as we already done in the breaking system, we process this photo, extract all the faces, and in addition, in this case, we classify each photo based on the quality of the faces, and we assign each photo to one of the 3 categories. Then photos of each category are selected to create challenges of increasing difficulty and to measure the user's ability to solve them. As you can see, even graphically, this resembles the mechanism proposed by Facebook. In addition, after each page, we provide a feedback to our users, and we ask them to take a simple questionnaire. Our study involved 141 users coming from 14 different countries, the majority from Italy and Greece, with age comprised from 20 to 40 years. And from these users, we were able to collect 4.5 million photos and almost 5 million tags, the majority of them belonging to the simple category. Our users took a total number of 1,044 distinct tests, and what we saw for the simple and medium category is that they obtained great results from the users, with a success rate that span across 98 to 99%. So not only the simple category that is used now by Facebook, but also the medium one with photos of pure quality is still usable by humans. Then, regarding the difficult category, users obviously encountered more problems, but also score surprisingly well, with the success rate that decreased only until 82%. So people are able to recognize their friends just as good in both standard social tests and tests with photos of pure quality. So we recommended to Facebook to use photos of pure quality in their tests, as this will increase their security without affecting the usability of the overall system. Conclusions, we have demonstrated the weaknesses of this mechanism, and we revisited this approach, proposing a new mechanism that is still usable but robust against automated attacks. This was a joint work between Politecnico di Milano, Ford Research Center, and Columbia University of New York. Thank you.
Okay, thanks. Any questions? Okay.
Hello, thank you.
Hi.
If you're looking to extend or continue this research, might I make the suggestion when you're doing the casual attacker, you can increase the refinement level as well as the output of the friends mapping. If you also use Facebook graph search to correlate likes as well as tags.
That's a really nice idea, yeah.
Yeah, so check out FB Stalker. It's part of the open source intelligence stalking open source project. And there's some stuff there you could use, I'm sure.
Cool, thank you.
Okay, further questions? Okay.
Yeah, more general question. If such a mechanism is used, how does it treat people who have no friends?
People with no friends.
No friends.
Yeah, actually, statistics show that a user on Facebook have 240 friends on average. People with lower than 50 friends cannot use such a mechanism of defense because Facebook trigger this mechanism only if the user has at least 50 friends.
And second problematic group, what about celebrities?
Yeah, that's a problem. The other problem is the opposite of zero friends. It's people which have friends with a lot of other people, or which people which accept friend requests from everyone just to increase the number of his friends. Well, these people can have problems using this mechanism itself, and not only for a software, but also the legitimate user. Yeah, this is a problem taken into consideration also by Facebook. I don't know if this mechanism is proposed to celebrities or people with a greater number of friends, but this is a usability problem, of course, yeah.
Thanks.
Okay, any other questions? Okay.
With this mechanism, do you only use photos that are tagged, or also the ones that are not tagged but have people in them?
Excuse me, can you repeat?
There are a lot of photos that where the people are not tagged, but they're on it. Do you also use the not tagged photos?
Okay, I see. Actually, Facebook used tagged people to create the test, and there are cases in which tags are wrong. Facebook, in some tests, proposed photos in which there was tagged a can of Coke, for example, as one of the friends. This is there's some noise that is introduced in the data set, also because people tend to tag almost randomly on the photos. So we had to correlate the distance of every tag to the closest faces in order to be able to remove some of the errors. If a face is too far distant from the closest tag, then this tag is discarded.
Okay.
Just a question about those users that trolling for other people's information. So the users who try and befriend other people, and you often see requests. Do you know how the mechanism works to prevent those getting further access via friends of friends? Does blocking those profiles then prevent the downward stream of flow of information, or do Facebook not prevent the friend-of-friend link if you've blocked somebody who has become a friend?
Well, actually it doesn't block this.
Poorly explained, sorry, but I think you got it.
Yeah, the problem is that even the chain is strong as its weakest link, in the sense that you can have all of your friends really sensible in security topics, but just one friend which is not so aware of the risk implied in his behavior on Facebook can hinder all the effort taken by the others. Because if you are friend with a person on Facebook, then this friend can easily see all what you've done on Facebook. And if this friend has a malicious friend on this side, can still reach a portion of your data, and you can do almost anything about that, sadly.
Actually, specifically, there's the mechanism to block a friend request. Do you know if that stops the downward flow of information through the friends of friends? Do you know if Facebook enforce strict security there, if you've blocked the person?
Not that I'm aware of, no.
Okay. Further questions? Okay, so we are actually ahead of time. So we will go into the lunch break. Sorry, into the coffee break, and we'll see you all in about half an hour.